then our next speaker is Tobias Kippenberg, and he will talk about intercoherent mechanical oscillators, room temperature, quantum optomechanics, and collective quantum motion. Tobias, please go ahead.
Yeah, thank you for putting this together and for the invitation. I've thought a lot about how to structure this talk, and I've seen a lot of advances. What I thought to do actually is tell you a bit about, very briefly in the first part, just a little historical note on optomechanics. And I want to start the talk by mentioning, I was working at the MPQ actually some 20 years ago, and there was Gary Gabrielsa from CERN doing a G-2 measurement, coming in our lab and looking at optomechanics. And we were explaining to him enthusiastically with Albert what we were working on. And he was saying, well, Tobias, I tell you one thing. One day you'll wake up and realize you have been doing this for 20 years. Okay, so there's one paper that's almost 20 years. So I'll remember. Okay, after getting everybody a bit cheered up, I want to start just going back to some of the first 10 minutes to talk to you about the introduction of quantum mechanics and a bit broader perspective. Also linking some of the early work that I did at Kippenberg with Kari Vahala, and then actually I just spent telling you about two things that were quite exciting actually in recent years. So first of all, mechanical systems are part of our daily lives. They are technology. They are used in timing. I come from Switzerland, so they're used in quartz crystal oscillators historically. They're used for accelerometers. They're used in atomic force microscopes. Again, I come from Switzerland, so we're very proud of having some of the pioneers in AFM here. And of course, they've also been used in some of the most, I would say, remarkable experiments I find of human mankind, which is gravitational wave detection. It's sheer remarkable to think that you can actually measure displacements of a mass that's been moved by gravitational wave. And so mechanical systems are really span this network from science and technology. They have a speed of sound that's much smaller than speed of light. They can have high Q, also room temperature. That's actually what's used in the F-bar filters in your phone, where they're used actually in 5G, 6G, rather than electrical circuits. And what should hopefully be clear to everyone, but I want to mention it one more time, it's challenging to put this in a quantum regime. And it's challenging because of the low frequency. If you have a system that has a frequency of a megahertz, you need actually a temperature of 50 microkelvin actually to freeze up all thermal motion. And that's far below the temperatures of dilution refrigerators. So you need other techniques. And the other point that I'd like to make is that it's not just about cooling device, but also of course measuring its motion, seeing how it responds to environment, to forces. And here's the scale is set by a zero quantum motion of the oscillator. If you have a large mass, of course, then these become extremely small. And in the case of, say, non-mechanical AFM, already it's a typical fraction of a proton diameter. And so historically, what's very interesting is that there's, of course, a precedent of cooling systems and achieving very low temperatures, and that's really the field of laser cooling that started in the 70s by Art Ashton, Stephen Chu, that showed that you can use lasers to create kind of molasses, so viscous forces that can slow down the external degrees of freedom of atoms. This has also been extended to Hall traps, and you can cool ions down to the motional ground state. Dave Vine achieved this in the 90s, and it's really been ushered the era of quantum computing, because in fact some of the early quantum computers used actually the internal and external degrees of freedom of ions. And here, control that motion has been really pivotal. And so the question is, can you extend this to mechanical oscillators? And this is an old slide I showed many years ago, but I thought to pull it up. And really what's very fascinating to think about, especially from modern perspectives, is that already in the 60s, Vladimir Baginski was thinking about quantum measurements. And this is a heuristic saying that for every Western invention, there's one Russian who did it before. And it is also true, actually, in some sense, for mechanical effects of light. So what is really astonishing is that already in the year 1969, okay, so this is well before actually Art Ashton or Dave Wine, Demelt and Hensch and others were thinking about laser cooling. Brzezinski was proposing the investigation of dissipative quantum motive effects of electromagnetic radiation. And so I wanted to make sure that this paper is at least shown once here in this conference. I think I'm the second person to show it. So what Brzezinski was thinking about is how you can use radiation pressure to, in this case, create a viscous force. But he was not so much interested in a viscous force. He was really worried about something that the force can actually become not a force that is damping, but it's amplifying, and this leads to a parametric instability. And they've put here this calculation that is in his book actually, Measurement of Weak Forces. You can directly show very easily that this is a mechanical oscillator that's driven by radiation pressure, and if there's some retardation that comes through a cavity, that radiation pressure force can be viscous. So you can actually create a viscous force whose sign depends on the detuning. So those things are buried in literature in the 60s. And parametric instability actually is a real concern in LIGO. It has been observed in 2015 by pumping actually LIGO very strongly and seeing effectively the equivalent of a phonon laser, where you have a coherent amplification of mechanical motion. Now, what's sort of interesting to note is that about 10 years ago, before that, so already 2005, this effect actually was observed in microcavities, in very small systems. And this is perhaps no surprise. LIGO has 30 kilogram heavy mirrors. And if you go to kind of toroidal resonators, which at the time we're studying with Carrie Bala at Caltech, so these are miniature kind of whispering Gauge mode resonators, where light is continuously circulating. And these devices, you have on one hand an optical mode that can have a very high Q. So this Q actually is 100 milli, so the photon lifetime here is about 100 nanoseconds. The path length is about 100 meters that you wrap into this fraction of the hair. But what's also present, and this is completely obvious from today's perspective, is there's a mechanical mode. So this is like a wine glass that has a flexural mode that can actually couple via radiation pressure, because as the photon travels around the circumference, it changes direction. So you have 2 h per k momentum transfer per round trip. So this is kind of a natural optomechanical system. And this led actually to an instability that initially was thought to be thermal in nature, but it became very clear very quickly actually it's an amplification process. And so in some sense these microresonators are natural kind of optomechanical systems where optical modes are coupled to mechanical modes. And this we reported back actually almost 20 years ago. You can do other things with microresonators. I won't talk about them, but they're really kind of fascinating on their own right. You can also generate solitons and frequency combs, so you can even link them to metrology. But for the purpose of this talk, they provide really kind of a stepping stone into optomechanics. So what's important to be in the cycle resolve regime that I mentioned before, so they can have a toolbox now of control of a mechanical system, and you have either beam splitter, hematomy, or two-mode squeezer, and you can establish remarkable control in the quantum regime of these mechanical systems. And this has been really ushered by numerous kind of contributions of finding systems that have large optomechanical coupling, large quality factor, operational cycling regimes. One of the most successful platforms are these vacuum gap capacitors. And there's been really, from my perspective at least, really is very surprising kind of, plethora of explorations of really putting mechanical systems in the quantum regime. So from entanglement, from squeezing of mechanical motion, to observing quantum back action or the variational measurements we referred yesterday. There's also been a lot of theoretical progress of looking how single mode optomechanical systems, but also lattices, can be used to emulate topological lattices of phases of light and sound, and numerous other kind of theoretical proposals that have been made. Now, even though the focus also here yesterday was very strongly on quantum, let me still mention that over the years also explorations were made, and some of them are still very nascent, very emerging, but still there are applications also one could conceive possibly for the future. Let me just only mention two that I find rather interesting. One is to make a so-called quantum noise thermometer. If you can see quantum optomechanical phenomena at room temperature, you can use the quantum noise to make temperature measurements. This is not something completely absurd if you think about how actually fighter sensing works, or Raman thermometry. You lose Stokes and anti-Stokes sidebands, so the difference n+1, so the commutator, to make temperature measurements. And you can make very compact kind of tabletop devices actually with these low frequency oscillators that allow you to make temperature measurements that are self-calibrated. Another example that I find personally very fascinating is to make transducers. In this case, not from quantum states, but classical states. And this is an example actually I've picked here from Eugene's work, where some years ago he made a transducer that was able to measure effective electric fields generated inside an NMR, and where there are very large magnetic fields that typically kind of would interfere with the electronics. So have an optical readout that you can also put in a large magnetic field where fields are switching is an example where some of these optomechanical techniques of readout actually can be beneficial. And again, many of them are early nascent stages, but still there are explorations that have been made, and I want to highlight these two as interesting examples that I find. Now, another aspect that was what can be observed is one can look at displacement measurements using these optomechanical systems. And this is a graph actually I took here from Vivek Sudhir's thesis. And what he's shown is that plotted here is a displacement sensitivity of that are made on mechanical systems of all sorts, and it's just this function timeline. And what's actually rather interesting is that it's been historically very challenging to kind of make measurements, basically at the standard quantum limit. So let's not go to the definition of standard quantum limit, let's just take a very heuristic one. Okay, let's look at the signal-to-noise ratio of 1 to be able to resolve the zero-point motion of the oscillator. Historically, with electronic, atomic point contacts and squids, it's been typically challenging to reach the level of a zero-point motion due to electronic noise, and that's really changed actually with optomechanical systems. And this plot here ends already in 2015. Now, actually, I would have to extend it much further down. So I think LIGO is operating right now, I think 9 or 10 orders of magnitude actually below the standard quantum limit. So it's really possible to measure or to have a position variance in a measurement record that is far below the zero-point motion. That's and this progress is really due to these optomechanical systems that kind of use optical readout rather than electronic one. And so in some sense, what all these experiments are realizing actually is the Heisenberg microscope. I mean, these are measurements where the product of imprecision and back action really approaches very closely H bar. And this provides me also now with a jump to some contemporary research. So we have been interested to ask the question, can we make these Heisenberg microscopes really at room temperature? So in the presence of actually a very large thermal bath. In order to do that, what you need is a mechanical oscillator that's very well isolated from the environment, so where the force noise from the environment is small, but also where the back action is correspondingly large and really dominates the thermal force noise. And so this provides me now a jump to my first kind of topic I want to go through. Let me see if I'm doing this time. Okay, 12. And I want to tell you about work that I had the pleasure to do with Niels Engelsen. I put up his picture because actually he's also here at the conference, so if you have questions, then please also feel free to discuss this work with him. And so this was work where we were motivated by the question, can we pursue quantum optomechanics at room temperature? So alleviating the need for cryogenics. And there's been 2 examples where this has been possible before. One we'll hear about actually later on from Marcus. This was trapped particles. And trapped particles in laser beams, and also these optically spring mechanical oscillator that Nurg has introduced, they share one thing in common. They can be the mechanical rigidity. Okay, so mechanical properties are dominated by light field. So the eigenfrequencies here of these particles trapped in laser field is given by the optical potential. And the same actually for these LIGO mirrors. So the innate frequencies a few hertz, and then you spring them up to a few kilohertz by the use actually of an optical spring. So a mechanically mediated or optically mediated restoring force. And so we have been motivated for many years to kind of make room temperature quantum optomechanics with kind of these solid state systems that are anchored where, say, the innate properties are mechanical in nature. And this has a couple of complications. First and foremost, the mechanical quality factors. So these systems are basically coupled to the environment, so there's dissipation. In order to be observed quantum optomechanical phenomena at room temperature, what you really need is a thermal decoherence that is a rate that is smaller than your back action rate. So a number of kind of challenges, and what really has helped us is this astonishing progress actually in making high Q mechanical oscillators. And what this has been possible due to the fact that you can use thin film stress mechanical oscillators. This was already known back in 2006, but I worked at Craighead. Then Jack Harris showed you can even use just TM grid membranes, which have surprisingly high Q. Initially, there was confusion in the field. Are the two-level systems somehow absent? No, the TLS are not absent. This material actually has a low mechanical quality factor, but it's this dilution that happens due to tension that's been first studied in the gravitation wave community that allows actually to take these quality factors from a few thousand in their kind of bulk acoustic propagation loss form all the way to Q factors now that can be literally 3 billion at room temperature in these very simple kind of perimeter modes. And I think there's even devices that are higher using hierarchical structures that can make hundreds of quantum period oscillations at room temperature. Now one short explanation, I think it's still kind of very interesting to think about the concept we're using here. And I want to show a very simple toy model, okay, that's been developed by Gareth Steele with Sergei Fedorov, that really helps understand actually how this works. So if you have a typical, say, spring mass model, okay, you can model the spring being lossy, so it's a damper, and then your quality factor is so-called the inverse loss angle, and this is just the retardation between stress and strain in the spring constant that's assumed to be complex here. Now, if you don't have an in-plane motion, but rather an out-of-plane motion, then let's look at the following. You can look at the elongation of the spring, okay, due to the motion. So in the in-plane case, the elongation delta L is just linear in displacement, okay, that's very obvious. But in the case where you have an out-of-plane motion, there's something very interesting happening, that the change in the length of the spring is actually quadratic in y. And so, be cautious with our terminology now, but this is a geometric nonlinearity. So the elongation of the spring being quadratic actually in displacement, this gives rise to loss dilution, which is very non-intuitive, because it means that the quality factor actually of this mechanical oscillator is in fact larger than the bulk acoustic propagation losses. So take a piece of silicon nitride that's bulk, propagate 100 kilohertz wave through it, and we dissipate it very quickly. The same material strained can give suddenly quality factors of billions. And it's, so in that sense, it's a concept that in condensed soft matter physics is called floppy mode. And why is that these are floppy modes? Because actually their frequency will actually go to zero in the limit of large stress. So that's actually kind of the underlying, kind of point of loss dilution. This loss dilution can be augmented by, as Albert explained, by basically mode shape engineering, removing kind of the clamping losses and changing the scaling law of this loss dilution. You can also have what we call sub-wavelength soft clamping, where you can have these hierarchical structures or kind of these perimeter modes, which you can think about as acoustic whisperingality devices. And these can now have quality factors of 4 billion just at room temperature, and they're extremely simple to make. But again, intrinsic quality factors are much smaller. So, so these are explicit sensors, and we heard of this already, but you cannot always choose what to sense. And one of the surprising discoveries we made recently is that, first of all, we can make very high Q devices. So this is an example of a hierarchical membrane. It has a string. It has 100 kilohertz frequency. The quality factor here are close to 1 billion at room temperature. So you have zetton, hertz, few hundreds force sensitivity. And please note the scale here. These are ring downs that are extending actually for 6 hours. Okay, so done in a stroboscopic way to not be sensitive by laser heating. Now you can integrate this with optical cavities. The way this has been done actually is using photonic crystals. So here there's 2 photonic crystals that form a supermode that couple to the mechanical motion. But what we found out, very surprisingly, is that due to this very high Q, you are sensitive, okay, already to non-contact friction at distances that are vastly larger than what you would expect from reading atomic force microscopy literature. In AFM, non-contact friction happens at a few tens of nanometer. Here already, with a gap of a micron that you can see already with a bare eye, we start to see non-contact friction. So despite having these exceptionally high Qs, okay, we cannot easily make an optomechanical system operate in a quantum regime at room temperature because of actually non-contact friction. And so in some sense, this reminds me of a slide that I showed actually, I think in the first GRC. This is really like the Hydra. You find, you prove one metric in the system, but there's something else you find. And so clearly this near-field coupling that we're trying to explore to make a large coupling to the mechanics actually is not the way to enter the regime of quantum optomechanics at room temperature. And so what we have resorted to is actually work where we just put a membrane in the middle, and this technique really segregates now the mirror from the mechanical system, but you still have to deal with other challenges. And these challenges are non-energy induction that we'll not talk about, photothermal effects, so just the heating of the membrane due to residual absorption that causes a photothermal body force that can drive the mechanical motion, and cavity frequency noise. These are probably the world's most sensitive phase noise analyzer. Any classical noise actually imprints itself as motion. And you have to ensure that the cavity that you use to interrogate the mechanics actually is lower noise than the frequency noise that the motion of the mechanics induces. And so, so we found 2 ways recently to make progress. So the first is heating of membrane typically what's been done is you use these perforated devices, so to create a phononic band gap. And there's a beautiful work here from Hawaii that show that you can actually go and modify the speeds of sound actually by making density modulation. So these are not perforated membranes, but these are membranes actually with very small kind of deep sub-wavelength kind of acoustic wavelength kind of protrusions that you can use to create a phononic band gap. And they have one key advantage, which is that you can retain the stress, so you can have slightly higher quality factor, but also you have significantly reduced thermal instabilities. And with this, you can increase the power handling and the quite dramatically compared to, say, the soft clamp devices that have used here perforations. So we have devices of Qs of 200 million. We've seen as much as 800 million in these. And the next question is, okay, can you actually read this motion out and really create a Heisenberg microscope at room temperature? And so what has been traditionally another limitation is cavity frequency noise. So we can make mirror with 7 digits of 9s behind the comma, but the problem is these mirrors have intrinsic thermomechanical motion, Brownian motion of the surfaces that impede basically distinguishing the signal, okay, the frequency noise from the mechanical oscillator from that of the cavity. And so here's a truly ingenious method that Guanhao Wang's postdoc at Harvard came out with. And so he took one of the mirrors. So this is a curved mirror, this is a flat mirror, and he computed what would happen, okay, to the band structure, okay, of the mechanical modes. All the mechanical modes this mirror has, so this bulk mirror, and he came up with a very simple square lattice here, where he created a mechanical band gap, okay, at 1 megahertz. And now, how do you create such a mechanical band gap? He literally took the mirror and actually just diced it. The same dicing used in the clean room for single-looking chips. And surprisingly, the finesse of these mirrors actually did not change. So we still have here a finesse of close to 100,000 in this cavity. But now, what happened is that the cavity frequency noise dropped from a level of about 10 hertz per root hertz down here to 10 to the minus 2 hertz per hertz. So extremely kind of low values of 2 orders of magnitude improvement. So it's not something you can universally apply. It's only a certain spectral region you can clean up, but it's still quite surprising to me. You can reduce cavity frequency noise by 2 orders of magnitude over such a wide band gap. And so with this now, you can assemble a mechanical system now, density modulated membrane, place it inside these phononic engineered mirrors. And you can observe, if you take into account, as I said, this intermodulation noise, which I won't talk about, you can actually observe squeezing. And this can be calibrated very precisely. So you block the beam, you have a reference power on the photodetector, that's the red line here. Then you actually start measuring, change the Hohmann angle to between phase and amplitude quadrature. And what you see actually is here the squeezing over a few tens of kilohertz due to the effect of radiation pressure quantum noise. So, so this shows that we can really build these Heisenberg microscopes at room temperature with these ultra-coherent mechanical oscillators and employ all these progress made actually in the last years. And what we dream of doing now is really try to observe quantum cyclone symmetry, ground state cool, and potentially even mechanically squeeze actually at room temperature. Now, I'll be cautious. I don't think the applications of mechanical squeezing are around the corner. But to me, it's just a fascinating prospect that you can take a bulk device, you can see the microscope, and actually squeeze it at room temperature. So, so that's what we're really excited about to do in the future. And the way to get there is to employ other techniques like strain engineering to increase the quality factors even further. Okay, so the other thing that we've been fascinated by is the question. We've studied now a lot. One mechanical mode coupled with one optical mode. What about lattices? What about making really complex systems? And a part of this motivation, even though we haven't fully explored this, is the famous saying, more is different. So more is different, made by Vlanessen, refers to the fact that even if you understand the physics of one system very precisely, the moment you have a large number of them, you have immersion phenomena. And so the question is, can we make large, complex optomechanical systems and look at lattices? And so what's shown in the background here is an image that we devised a number of years ago. This is the two-dimensional SSH model. So it turns out an matter physicist had studied this. It's a model of strained graphene. And for instance, in this case, we could actually use the optomechanical interaction to measure the edge modes that we're making in the electromagnetic structure. So what are you looking at here is the following. These are vacuum gap capacitors. So, speaking after John implies that they have introduced a remarkable system to study optomechanics. In order to make lattices, there's one aspect that we had to work on, which is you want to make really identical unit cells. Identical unit cells meaning an identical LC, an identical mechanical frequency, and ideally also very low damping rates. And so the way we've done that is we have overcome kind of two challenges of this approach, which is to make first of all the mechanical and microwave properties identical by re-engineering the fabrication process, and then extending from 2 or 3 to very large layers of mechanical modes. And so I won't go into much detail, but evidently a lot in optomechanics also depends on making systems that have exquisite mechanical and microwave properties. So this is our vacuum gap capacitor. It's made in a slightly different fashion, where we can very accurately control the gap between the lower and the upper kind of mechanical plate that form the capacitor. They're separated here by typically about 100 nanometer, and their dimension here is about 50 micron. And with this approach that allowed us to have better gap control in a flat top surface, we could obtain large quality factors. Now I say large because these are not as large as what we can have at room temperature, but they're still about 14 million. But now these devices are operating at millikelvin temperature. So you have a thermal decoherence here that is vastly lower than what you would have in these room temperature systems. Now, pleasingly, actually, so we're still trying to understand actually why these quality factors are that high. So there's still some aspects we don't understand about them. What you can do now is you can look at the thermal decoherence. And so the way to do that is you can first cool with a red side and pump these devices to ground state. And then you can read them out, and the readout is actually best done using the optomechanical amplification, a scheme that Conrad first implemented, which works remarkably well, gives you very low added noise, just 0.8 quanta. And what you can see here is the variance actually of the motion of the mechanical oscillator is a function of time. So we start out in the ground state, here it's about 97%, and we start actually to thermalize to the equilibrium of about 200 quanta. And from this curve here, by fitting it, you can see we have basically a thermal decoherence rate of about 7 milliseconds. So that's kind of a number actually is quite low. So this is comparable to what you'd have, say maybe some of the rudimentary ion traps. It really shows that the system is very well decoupled from the environment. So you have effectively 7 milliseconds to do operations and see the evolution of the oscillator. And one of the experiments we did was actually to look at squeezing. Squeezing is phase sensitive, so here you'd be very sensitive actually to frequency fluctuations during the 7 millisecond time. And one of the things we found out is that we can not only squeeze the oscillator, but in fact the dephasing time actually, or dephasing rate is vastly lower, okay, than the thermal decoherence rate. And that allows actually to track this squeezing as also a function of time. And here, for instance, we start to squeeze the oscillator to about -3 dB. It's released at time 0. We see how the squeezing actually starts to be lost as the environment kicks in and destroys actually the squeeze state. So, so these platforms work remarkably well, have very low decoherence. The mechanical systems or mechanical oscillator quality factors and frequencies are very close in frequency. I will comment in a second. And this allowed to do one last experiment that I want to share that we recently completed. And that is, we want to look at collective phenomena. Admittedly, these are very simple collective phenomena still, but we thought it was a particularly nice example. So what these are 6 mechanical oscillators, and they're coupled to one common electromagnetic mode. And what we wanted to do here is to cool not an individual mechanical oscillator to ground state, but we want to cool the collection, so collective mode. So how does this work? So the idea here is to have 6 mechanical oscillators, so axon there, coupled to one microwave mode, and use this one microwave mode here as a dissipative reservoir to cool the motion all the way to the ground state. And so the way this works is, if you look at the physics of this collective mode, then if you have multiple mechanical oscillators with indistinguishable frequency coupled to the same cavity, you get a root n enhancement actually of the optomechanical coupling rate. And this is because you're coupling to a collective mode. And so in our case, we should see a 6-fold enhancement of all the optomechanical dynamics, be it the coupling rate, be it the cooling rate of the system. And so we've realized this system, again, by taking actually 6 LC cavities, all mutually coupled, So the topmost mode and bottommost mode, one is bright and one is dark. One we can use actually dark mode we can use for cooling, the bright one for readout. And what you can do with this system now is really watch this transition actually from individual oscillators to collective motion as you start to increase the pump laser here. And so we start seeing initially oscillators that are all individual. There are 6. They have a frequency spread of about 0.1%, so they're distinguishable. When we start increasing the optomechanical damping, we start to see a transition actually of that system to the regime of collective dynamics. And how does it look like in the experiments? We start to see the damping rate that initially increases for all mechanical oscillators, and then suddenly something surprising happens. Even though you increase the cooperativity, some modes actually see less optomechanical damping, and actually it's reducing. Except one mode, the collective mode, and that collective mode emerges then and goes into strong coupling that you can then easily see also in the strong coupling curve. So here's a detuning. You start to see the typical kind of V-shaped curves for the strong coupling, and very surprisingly, all these modes that initially were cooled in the recoupling regimes in the collective regime start to disappear again. So it's a very counterintuitive regime. The other aspect that is surprising about this regime is, and you can start thinking about this, is you can cool a mechanical oscillator. This cooling works also well, so you can cool the systems to the ground state and also do cycling and symmetry. But here what happens now is that the ground state that you've created is not one of an individual oscillator, but actually of this collective mode. And so if you were to measure the temperature of each mechanical system, it will reduce by 1/6. So it will still be hot, but the collective mode actually is in its ground state. So it also challenges a bit our understanding actually of what zero motion is and how we can interpret this. And you can also even go into the strong coupling regime and also there observe cycling and symmetry. So with this, I've used up the 31 minutes according to my watch. And thank you for your attention, and again, thanks for the invitation to this symposium.
Questions?
Thank you very much, Tobias, for this very interesting, exciting results. Related to the last part, this excitation of the collective modes. Do you engineer a bit the dissipation, or because your kind of coupling depends on sometimes also on the dissipation? So you take the frequencies, all of them equal, if I understand correctly.
Yeah, that's right.
And the dampings. So do you have a little bit of engineering in order to avoid the dissipative couplings between them?
So the damping actually in this case, in these devices, is still only controlled very rudimentarily. So we do a bit of what we call clamp tapering. So we can actually change the aspect ratio of the clamps. I should say we still don't have a very good understanding of what exactly loss dilution factor is in these planar devices, especially also as temperature reduces, we don't know exactly what the strain is that we have generated. But aluminum that we're using here as a top plate is amorphous, it has grain boundaries. In that sense, there must be a significant amount of basically loss dilution occurring, otherwise we would not see these quality factors. One of the things we wanted to try, so we recently came across niobium. We found out actually that at low temperature there can be actually as much as 1 gigapascal stress. And so for aluminum, the yield stress is about 200 megapascal. So we think with niobium top plates, probably we could increase these quality factors probably substantially by increasing the stress.
Cool results, Tobias. Have you thought about doing the dissipative squeezing trick for these collective modes?
Yes, that's what.
So if you pump on both blue and red, you would end up with some interesting multi-mode entangled state.
Yeah,
It seems like
so it's next we have this is the first thing we were discussing in the team that we should do next, and there's just a very technical issue of that current sample that we have too little. So we could do this trick, but the problem is the readout right now, and we need a different design actually to be able to access the quadrature. So it's a bit similar to my comment saying each of the mechanical oscillators is only reduced in temperature by 1/6 because we don't have access to that. So we would need another circuit that measure each mechanical oscillator to prove that. And similar here, we could apply the scheme, but we would have to think about what are observables. But this is actually one of the things that we want to build next, is really to see if we can also squeeze collectively.
Tobias, thank you. Brilliant as always. Question on the phononic band gaps for the low noise mirrors. So how low do you think you can push it in frequency, and how large do you think you can make the gap? So what are the ultimate
so I
limits?
think for LIGO is probably not an option, but where is it? So I think it's on our case the mirrors here you have the dimension. They're still pretty small, so they're 2 millimeters. So we looked at 100 kilohertz, and that looked for us actually kind of challenging to do. So, but again, we've seen, for instance, Nurj's talk, and she showed a 300 meter long reference cavity. So it depends really on what the setting is that you have in mind. But bear in mind, it's always kind of a narrow band kind of cancellation that you have. So in that sense, the dream would be broadband suppression, crystal mirrors. So this is maybe the second best option.
Good. I don't see any more questions. Let's thank Tobias again.